Hello, and welcome to Lab 2, Part E, Close-Up View of the West Coast. In this section, we will take a closer look at the plate boundaries of Western North America. These three lithospheric plates include the North American plate, the Pacific plate, and the Juan de Fuca plate seen in between the two major plates. We will focus on this area to help you gain a more dynamic perspective on how plate tectonics influence the surface appearance of our planet over large geological timescales. To begin, open Google Earth Pro, turn on layer Part E, and turn off layer Part D. Then double-click Part E, and Google Earth will zoom to the coastal region of Western North America. Within this area, all three types of plate boundaries are present: divergent in red, convergent in blue, and transform in green. Let's begin by looking at the world's largest transform boundary, the San Andreas Fault. The San Andreas Fault is an active major plate boundary where the North American and Pacific plates slide past one another. The relative plate motions are marked by the arrows. However, the absolute plate motions are quite different. It's a little misleading viewing a 3D spherical surface on a 2D map. On a 2D projection, the absolute plate motions are indicated by the large arrows, and they may appear to indicate that the North American plate may be subducting beneath the Pacific plate. However, their absolute directions of motion are reported relative to the Earth's axis. Additionally, notice the speed of the individual plates. The Pacific plate is moving more than 3 times faster than the North American plate. Thus, the relative or apparent plate motion translates into opposite directions. Next, assuming that these plate motions continue into the geologic future, then San Diego, which is situated on the Pacific plate, will continue to move northward, and cities like Oakland, that are located on the North American plate side, will continue to move southward over geologic time. Finally, if we follow the trace of the San Andreas Fault to the north, then we notice that the northern tip of the fault forms the lower transform boundary of the Juan de Fuca plate. The Juan de Fuca plate. The plate boundaries to the Juan de Fuca plate can be seen in the lithospheric crust along the northwestern coastline of North America. When we turn on the plate boundary model layer in Google Earth, we can better examine the individual plate boundaries, again with divergent boundaries labeled in red, convergent in blue, and transform in green. Let's begin by looking at the relationship between the Pacific plate, the North American plate, and the Juan de Fuca plate. Plate motions. The Juan de Fuca plate is being created by a spreading center. As magma pushes its way to the surface, new plate material is created on each side, pushing the plates apart. The transform boundaries create fracture zones that connect the offset portions of the divergent boundary. And as the relatively dense or heavy oceanic Juan de Fuca plate moves eastward, it subducts beneath the less dense continental crust of the North American plate. In the process, a deep oceanic trench is formed along the convergent boundary. Volcanoes. As the Juan de Fuca plate subducts beneath the continent of North America, an inland continental arc of volcanoes are created. This is because the oceanic plate is saturated with water and other volatiles. As the oceanic plate subducts to increasing depths, pressure squeezes water out of the plate and introduces it into the mantle, lowering its melting point. Thus, magma ascends to form an arc of volcanoes parallel to the subduction zone. An example of an inland volcanic arc is the Cascade Mountain Range located along the Pacific Northwest of the United States. This concludes Lab 2, Part E, Close-Up View of the West Coast. Complete Part E in your lab assignment, and please address your questions to your lab TA.